Molecular formulas, little bit different, but kind of the same to what we did the last time when we met. Last time when we met, we dealt with empirical formulas, which dealt with, like, if I had a compound, say C6H12O6, is that the empirical formula for glucose? No, because it can be simplified down to look like this, where we have, okay? So empirical formula, again, when you're looking at a molecule, we want the smallest whole number ratio. Now with molecular compounds, that would be the molecular compound for this empirical formula. Now the bad news is, this is the empirical formula for many compounds. It's not just for glucose. There could be other things that have like 12 carbons, 24 hydrogens, and 12 oxygen. But this is and does represent the small total number ratio for a compound that has this ratio of elements. So today what we're going to do is we're going to take empirical formulas and change them into molecular formulas. Awesome. And there is an equation that I had on here that looks like this guy right here. And this is what's called our multiplier. And this will make more sense once we actually start doing some of the practice problems. But what this is, it's a multiplier. So like I had over there the C2 or the CH2O, what we'll do is we will find out what our empirical formula is, and then whatever our multiplier is, like in that last case, it was a 6. So by doing that, that gave us our C6H12O6 compound. The way that we can determine that value there, or the N, is by taking the molecular formula mass, the molecular formula of this compound, and dividing it by the empirical formula mass. So in all the cases, you will be given the molecular formula mass. It'll be given to you. You will get to calculate the empirical formula mass. That's fun. Let's do a practice problem. And it states, the empirical formula for a common drying agent is P2O5. The molecule has a molar mass or a molecular mass of 283.88 grams per mole. Find the molecular formula for the compound. So there's some information that's given to you here. What information do we have? Yeah, we've got the empirical formula. So that's really nice because you don't have to calculate the empirical formula. It's already been given to you. And sometimes I'll be nice like that and give you the empirical formula. Not all the time, so don't count on it. So all that work that you did yesterday to determine the empirical formula, and we'll get to do it again today, has already been done for you. So there's your empirical formula. Also, we're given the molecule has a molar mass of 283.88 grams. So to find the molecular formula, what we're going to do is we need to find out what the multiplier is. So we need to find out what this N value is. So again, N is equal to the molecular formula mass over the empirical formula mass. Okay? So again, the molecular formula mass will be given to you, and it's generally the bigger of the two values, if not equal. And then the empirical formula mass is the smaller of the two, where you get to calculate it. So looking at this, move you over, actually down. Okay. How can we find out what the molecular formula mass is? Or does anybody know it? 283.88. Good. So we have our 283.88 grams. And how can we find the empirical formula mass? Yeah, do what we've been doing. Find out how much that weighs. So we have how many phosphorus? 2, which is 30.97, plus we have 5 oxygens, and all of that weighs something. 141 point, what is that, 94? Anybody get that? Okay. So we'll take that empirical formula mass and put it right down there. Divide those two, what do you get? Yeah, and as a heads up, the N or the multiplier has to be a whole number. So in this case, it gives us a value of like 1.99, what is that, 857? So 2. So if we have, our multiplier is 2, let's get this out of the way, bring her down here, get that out of there, and we put a 2 there, okay, for our value there. What is our molecular formula? You got it. P4O10. Okay? So here's the empirical formula. There's the multiplier. There's your molecular formula. We don't want to reduce it because the empirical is the smallest one-number ratio. Molecular is what it is. Natural form? Sure, yeah. I like that. Do what? Why do I have an arrow? I don't know. It just went over there. Let's get it out. All right. So number 2. Everybody good with that? Okay. All right. Number 2. Hydrazine is a widely used compound. Awesome. Well, hold on, you're going to learn something here. It can be used to treat wastewater from chemical plants, removing ions that may be hazardous to the environment. We want to keep the environment happy. We talked about that earlier. It can be used in rocket fuels. Awesome. And it can help prevent corrosion in pipes for electrical plants. Now, isn't that awesome?
Sure.
That's what we call garbage.
I told you. Why was that in there? Hold on a second.
Because in life, you're going to be given a lot of distractors, and you have to decide what's important and what is not important. So that's my job, to help you decide what's important. I know it's all important to you, but for this question.
And it's not important.
All right, so here the question says, in a 32-gram sample of hydrazine, there are 28 grams of nitrogen and 4 grams of hydrogen. Is that important? Yeah. Yeah, that's pretty good. So we'll start off with our 28 grams of nitrogen. And we want to find out how many moles we have of that. And we also have 4 grams of hydrogen. Because in this problem, it did not give you the empirical formula. And it says, continuing on, it says the molar mass of the molecule is 32 grams per mole. What is the empirical formula of hydrazine? And also what you can't see is also determine the molecular formula too. Okay. So we'll determine what the empirical formula is, and then we'll find out what the molecular formula is. So in this case here, we want to find out some moles, right? Just like what we did last time. And hydrogen, OOA. Let's get some numbers there. Now again, these are mole amounts, so don't round these. So 1.998, we'll say 6. 32? What about the 32? Yeah, so that's the total size of the hydrazine.
Oh, so that's a compound.
Yeah, so we're going to find out what the empirical formula and molecular formula for hydrazine is. It's a good day. And then we get 3.9, let's see, 9, is that 6? 8, 3? Yeah. Okay, so there's your mole amounts. And again, we don't want to round that too much. So what do we want to do now? Yeah, divide it by the smallest number of moles. So in that case, that's a 1. And this is very close to 2. Okay. So what is the empirical formula for hydrazine? 1 N and 2 H's. Good. Okay, so we have, that's our empirical formula. So now to find the molecular formula, bring her on down. Okay, whoa, come here, N. Okay, so we're going to find out what our multiplier is here. So let's go. N is equal to, do we know the molar mass for hydrazine? Yeah, 32 grams per mole. So we'll put that in there. And do we know the molar mass for the empirical formula?
Yeah, we can find it.
We need to find it. Very good. So we'll go, there's 1 hydrogen, I'm sorry, 1 nitrogen and 2 hydrogen. and that's like 16.20028 Okay, and that's very close to what? 2. So we can say, okay, well, there's our multiplier right there. So what's the empirical formula? Or I'm sorry, the molecular formula.
N2H4.
Look at that. Okay, so we found the empirical formula, and there's the molecular formula. Isn't that awesome? All right, so let's see here. So you can determine that. Again, for the molecular formula, we need to use our multiplier. And again, the molecular formula mass on top over the empirical formula mass. You'll be given the molecular formula mass. You need to determine what the empirical formula mass is after you find the empirical formula. All right, so let's continue on with hydrates. So the 5s are part of your homework. Hydrates. Next Tuesday, I think it is, we'll be doing a lab that is working with a hydrate. And what a hydrate is, it's some compound, it's some molecule that has water chemically attached to it. Okay? And generally, we're looking at some number here. And so for every molecule, there's some water molecules chemically attached to it. That's why we call it a hydrate. If it doesn't have any water attached to it, we call that an anhydrate. Now, you don't need to know the term anhydrate, but it's nice to know what a hydrate is. And this lab, we're working with some copper, sulfur, oxygen compound that has water chemically attached to it. What we're going to do is we're going to heat it up and evaporate the water out of the molecule. It'll evaporate off of there. Actually, it'll be strong enough to break the bond. The molecule starts off as a nice blue color, and then when all the water's been evaporated off, it turns this white crystal. So we'll be able to determine how much water was evaporated from the entire molecule. So you'll get to have a lab next Tuesday. Hydrate, we're looking at a specific ratio of water for every molecule. Okay? Okay. Wasn't that a great lecture? So there's some examples. Let's look at a practice problem here. The practice problem asks, what is the formula for a hydrate that is 90.7%? This is actually strontium oxalate, not one of your polyatomics, so don't freak out about that. And 9.3% water. Now, what's nice about these is the formula has already been given to you. In other words, we have this percent of the strontium oxalate, and you also have a percent of the water. So you don't have to find the empirical formulas. They've already been given to you. But what we want to do is we want to find out what the ratio for that molecule to water is. So if you're given, say, a percent, what are you going to do with that percent? Change it to grams. Very good. So we're going to take our 90.7% and change it into 90.7 grams. And this is of the strontium, or the CrC2O4. And we want to find out how many moles we have of this. Now, strontium is not one of the elements we use very often. Strontium, there you are, 87.62. So 87.62. And there's 2 carbons. And there's 4 oxygen. And we'll find out how many moles that is. And we'll do the same thing for the water. So we'll find out that we have 9.3 grams of water. And 1 mole of water is 18.016. Use that enough, you'll memorize it. So let's find out what the molar mass for that guy is on the bottom. I have 175.64. Is that the molar mass for the strontium oxalate? Did you guys get that? Okay. So take that divided by that, and I get, so I get 0.516, we'll say 4 moles. Anybody get that? And then for the water, get something similar, 0.5162. Okay. So they're very, very close. So divide by the smallest value, which I think is that one. 162, 1, 5.162, which is 1. So our ratio is 1 to 1. So when I write this formula out, actually let's put it up here. Let's say that I'm writing my formula. It's SrC2O4, and then put this dot there. That represents that you have a water molecule chemically attached to it. And then what is our ratio? 1 to 1. So I'll actually put that coefficient of 1 there. You don't have to. If it's a 1 to 1, you don't have to, but I will do that. Okay. All right. So again, very similar to what we did yesterday, except the molecule has already been given to you, so you have to find the formula mass for that, and then we'll do our empirical formula stuff. Let's do one more. Actually, you try this one on your own. Don't peek up here. No peeking. Okay? Don't peek. Don't peek. I think my molar mass for the molybdenum compound is 352.18. Anybody else get that? So the mole amount is 1.2309, and the water was at 3.69. We'll say 1, 2. So, which one's smaller? Yeah, the top one. Which is 1. And which is like 2.9987, so 3. So how would I write this one out? MO2S5. Now that's not a time sign. That's a hydrate. 3H2O, right? Now, let me ask you a question. If you wanted to find the molar mass of this compound, because again, with the water molecule chemically attached to this molybdenum sulfur compound, how would you find the molar mass for this? Well, you know that this is the molar mass for the MO2S5, right? What would you do then? Treat this dot as a what? An addition sign. Very good. Because you have 3 water molecules chemically attached. So that's not a multiplication dot. That's a big dot. It's a big dot. Okay, that represents that is attached to that guy. Okay? So we do an addition sign, and then you do your 3 times the 18.016. Okay? No, I'm just saying, because you'll see it on the test. I'll ask you for the molar mass for this. But the thing is, I'm saying that this dot is not a multiplication sign. It is a plus sign. Okay, so you've got your water and you add it to your molecule. Okay? All right, So the homework. You got the 5s and what the heck? Ah, it's like the 5s.